Hello, class. Welcome to our 10th and final lecture. Today's topic will be unsupervised learning. So if you recall, in the beginning of the course, we introduced two branches of machine learning. There was supervised and unsupervised. And actually, for most of this course, we've been focused on doing supervised learning. And so whether that's been model evaluation, cross-validation, feature engineering, or the actual algorithms themselves, um, everything was oriented towards supervised learning. So today we're going to touch on the second family or branch of algorithms, which is unsupervised learning. So we'll start by talking about a little bit about why we might use unsupervised learning. So most of the algorithms and most of the projects we've been working on, we've always had a variable we've tried to predict, which is represented by the y variable. So whether it was a regression problem, such as predicting house prices, or a classification problem, like predicting cancer or diabetes, those were all oriented around increasing predictive power, improving our ability to get better accuracy. However, sometimes we don't have a particular one singular variable that we're trying to predict. Sometimes we have a data set and we just want to extract some sort of insights, maybe figure out some patterns. And unsupervised learning gives us a way to do that. So if you take a look at this scatter plot, we can see there's some sort of shape and pattern visually with a top clump and then some dots below. But unsupervised machine learning algorithms gives us a way to do this programmatically, mathematically, and so we might actually arrive and see something like this, which is pretty interesting to see that, there's three clumps or groups of dots, and they kind of each inhabit a certain subspace within this scatter plot, right? And so we're able to take something that is kind of without pattern and then produce something or pick up on the patterns that exist by using unsupervised learning. And again, we didn't have a particular variable we were training towards, such as, again, any of the variables we've talked about before, but just tell us what is kind of interesting about the data within here. And that's one reason to use unsupervised machine learning. Now, what is it? So instead of predicting a particular value or class, unsupervised machine learning can be used to help you understand the data more. It can be used to make inferences, to look at correlations, to find groups within data. It's also really handy to visualize data. So you saw how we were able to take something that was kind of, all monotone in one group and be able to break that into three groups and visualize them with colors. Two of the major techniques are principal components, which is a way to pre-process or to simplify your data set on a dimensional level, and often this is done to help improve performance on supervised models. The other technique is clustering, and so this is a broad class of methods, and it's used to help figure out within my data set, are there subgroups that may, each of the subgroups may be very different from each other, but within that subgroup, the data points within that subgroup are actually quite similar. And sometimes we combine these two techniques together. So recently I did this where I was tasked with trying to understand across our many offices and regions across America, how are our teachers doing, how are the offices doing, how are the students doing, and so that's a lot of data to look at. But we wanted to see, were there kind of particular regions or schools that were doing good, and maybe we can learn from them. We could also start seeing if there's systemic weaknesses in certain schools and regions. And so I took a data set that was 75 or so parameters, reduced it down using principal components analysis, and then I fed the principal components analysis into a clustering algorithm that then produced I believe, 8 clusters that we could then say, okay, there's 8 types of regions or offices that we can kind of put all these members into. And that encompassed all the original data set that was summarized into PCA. So sometimes we combine these two. You would do PCA and then do clustering. So that's kind of a word-heavy example, but we'll go deeper into both of these techniques, and I'll continue to reference that example. So, but going back to what is the difference between supervised and unsupervised? So we know that with supervised learning, we have the y variable that we're trying to predict. And that's kind of quote unquote the truth, right? So all the techniques we've learned from regression through tree-based models to neural networks to SVM, and all the measurement tools, whether it's cross-validation, accuracy, specificity, confusion matrix, the ROC curve, and the area under curve, all those things were centered around improving our ability to predict y, which is ultimately kind of the truth. In unsupervised learning, we don't have a truth per se. So if you look at the visualization below, we don't have circles and x's that we're trying to separate and figure out. Often we don't have that truth label, and we're just trying to figure out some patterns or some groupings that may be interesting. And so you can see in the unsupervised visualization, the data points were grouped together. And so the result of that is that unsupervised learning becomes a bit more arbitrary. There is no unified metric that all of us could objectively look at and say, yes, this is better, this is worse. One of the additional quirks, I guess, to unsupervised learning is that sometimes there's more data to work with. So if you think about supervised learning, it takes money or time to go out and actually figure out if a cancer cell, if a cell is benign or malignant. And unsupervised learning just may have a bunch of cells, and so sort of figure out how are these cells different? How do they look similar? But without actually going forth and saying, okay, this cell is dangerous and this cell is safe, or this house is sold and this house is unsold. So often you'll have more data to work with. Some use cases in business. This is used for marketing purposes, for segmenting your users. You're not going to be able to create, a product for every single user, but maybe you can figure out, my young users like this, or my West Coast users like this, and East Coast users like this. It's also used in biology to help with classification or hierarchy. So again, thinking about you have to create some sort of taxonomy, and if you need to group certain species or certain characteristics of, any sort of organisms together, what's a way to do that? Technology, recommendations engine. So, if you think about Netflix or Amazon, if I bought something and you and I are very similar, perhaps you'll also like the household appliance that I bought. Or perhaps you previously bought a product, and then there's a very similar product that a movie perhaps that you might like. So maybe they'll recommend that movie. So again, that's kind of looking at these patterns without having an absolute label of, yes, you would like this movie, or no, you did not like this movie. It's also used for anomaly detection. So if you think about many use cases, but including medicine, if you start grouping certain diseases, maybe their symptoms or their treatments, you can start seeing which ones are similar and which ones are dissimilar. Maybe there's a new strain or new virus that's emerging that behaves somewhat differently. And again, perhaps this is a brand new virus, so there's no Y variable for you to verify. And then also unsupervised is also a good EDA tool, so exploratory data analysis. This is a way to help you understand, again, how is your data shaped? How is your data shaped? How does it look? Is there a way to simplify your data and make it easier to understand? As you know, often we run into issues with data when we try to capture multiple dimensions, over 3. And so unsupervised learning is a way to help us reduce that. So we'll start by talking about principal components analysis. So principal components analysis it's kind of nicely worded. It's trying to find what are the main themes or patterns within your features that can be comprised in a smaller subset of new features. So if you think about it in the sense that a lot of your variables will probably be correlated, especially if you're working with maybe a very big data set that look with the data that's collected in a very similar fashion, perhaps. And so, is there a way for us to capture a majority of the variance of the learnings of the signal in the data with less variables? If you look at the example on the right, you're measuring education on the x-axis and then household individual income on the y-axis. And you see there's a spread, that's a pretty thick at times, the dots, but pretty tall, but there is definitely a pattern. It's up and to the right. So the more education you have, the more you're likely going to earn. And so when you think about this as some sort of socioeconomic well-being factor, the two kind of tell the same story, although there is some variance and some nuance that might be lost if you only use one. And so that's the basic idea, right? Like, if variables are showing similar stories, is there a way we can compress them into something new? And we saw this earlier when we were looking at feature engineering and feature reduction techniques. So we saw this with principal components regression, where we were taking a lot of variables, transforming them and aggregating them, and then producing a regression on those transformed and aggregated variables. And PCA is kind of doing the same thing. It's looking at all your variables and then trying to say, is there like some primary themes or components or group of variables that can be re-represented in lower dimensions. And because, again, we don't have a y variable, we don't have something to map, say, our income or our education against, we can't necessarily say one is better than the other. And so PCA is a way for us to group that together without really having like one singular truth variable. So a little bit more about it. When you think about not having that response variable, often the times when you do EDA in supervised learning, you're comparing that all your variables against that truth variable to see, okay, which one is really correlated, which one is good at prediction, or has some sort of relationship to the variable you're trying to predict. However, when we don't have a response variable, and now all our variables, perhaps we have 10 variables, are rather similar, and we don't weigh one necessarily more than the other, in order to visualize all that, we would need 45 plots, and that's on a two-dimensional axis. So you can see how this becomes rather inefficient and ineffective rather quickly if you have to start looking at these one by one using kind of like the naked eye to inspect all your variables and their relationships to each other. And so PCA allows us to find those components, turn those high-level number of predictors into a lower number of principal components. And so in the example I talked about earlier, we were looking at student performance, teacher satisfaction, financial performance, donors, a whole slew of metrics. And then we compressed those 70-odd metrics into a much smaller PCA set. And so we ended up, I believe, with 4 principal components. And so that allows you to then do, be able to plot and do something like this plot below, where you can see the first principal component and its relationship to the second principal component. So how do we do PCA? So it's important first before you do PCA to normalize and center your variables. And that means centering around the mean. So naturally your data is going to have some sort of difference between variable to variable, right? Some of them will be much larger, like the income number, and some of them will just be a percentage, like the bachelor degree education metric that we saw earlier. And so by centering and normalizing the data, we make those two metrics comparable, even though originally they were on different orders of magnitude, right? One in the tens of thousands and then one as a percentage. And so we will center the data and then normalize the data, and that's generally meaning that we'll set the standard deviation to 1 or some other value, but so that the data is comparable between variables. The other thing we do is then we start to measure the loadings of the individual features, and we want to constrain those loadings to 1 so that the sum of the squares of those loadings are equal to 1. And this is a way for us to then set up step 2, where we can then see which linear combination of those variables have the largest variance. And that sets up an optimization problem, which can be solved by using eigen decomposition. And this will then point out what combination of variables that can be stored. And this then represents the first principal component. And so that vector actually will help define what direction does the first principal component face. And so if you look at this example earlier, right, this is kind of pointing to kind of like 230, the first principal component, and it will pick up on the fact that all these data points are going up to the right and then negative to the left relative to the first principal component. And once we've done that and we've saved those loadings, we start looking at what variance remains among the remaining linear combinations that are not correlated with the first principal component. So we start looking at the second principal component, which is here represented by Z2. And by making sure that they're uncorrelated, we start looking at orthogonal features. So if you look at this chart again, this is creating a 90-degree angle. And so now we're picking up on the variance that is kind of pointing at, call it 1130, and runs a little more north-south as opposed to the northeast-southwest direction. And then you can kind of rinse and repeat, again, looking for uncorrelated combinations that are not reflected in the initial principal components to add additional principal components. So let's talk through an example. So there's a data set, the US arrest data set. It looks at all 50 states. It has arrests for murder, assault, and rape on a per capita basis. And it also includes a metric that represents urban density, so kind of a socio-demographic metric. And this simple example basically takes 4 variables, so the 4 on the left, and turns them into 2 principal components represented as the 2 columns. So go ahead and pause the video if you like, but take a look and try to figure out what's the difference between PC1 and PC2. So hopefully, you were able to pick up on that. PC1, there was the one that was kind of the outlier was urban pop, and murder, assault, rape all kind of were in the 0.3 to 0.8 range, 0.53 to the 0.58 range. And so it looks like PC1 is more about the arrest or the charge of the arrest, whereas PC2, if you looked, urban pop is very positive 0.87, while murder, assault, and rape are either negative or pretty low. And so it looks like PC2 is probably picking up on the fact that urban population is more of a, again, demographic, economic type indicator. There's a handy visualization tool that will help us understand this a little bit more. It's called a biplot. And so if you look at this, so you have two principal components and they're put on the X and Y axis. And you can see that murder, assault, and rape are pointing upwards for the first principal component to the right, and they all point about the same range. Urban pop also points to the right, but not as far, but more. And then when you look at it from the y-axis standpoint, the second principal component, the urban pop is way up, while murder, assault, and rape are kind of flat or slightly down. And so you can start seeing which variables are grouping together, right? Murder, assault, and rape represent something, while urban pop represents something else. You can also do this if you have three principal components. I don't think this is that great, but you see there's kind of a depth as well as a height and a width variable, and it gets trickier if you try to visualize anything beyond three. But you get the idea that you can create more than two principal components. It just becomes harder to visualize. So some things we mentioned earlier is like you have to make sure you standardize and normalize the variables. This is critical. So again, we talked about the income and the education attainment percentage example. But if we did not control, and you haven't seen the data, but if you did not control for the per capita statistics, which are an integer or a numeric value per, I think it's 100,000 population, whereas the urban pop metric is a percentage. So you had to control for that. But if you don't control for that, and you look at it on the right, you'll see that they behave quite differently. And there's a couple things going on. So murder and rape become much smaller, and assault becomes much longer. The other thing you'll note is that the blue points of the data, right? So they're much more compressed, and instead of taking up most of the chart, they're now all kind of hovering around the zero grid line. And part of this is because assault is a much more common charge than, say, rape and murder. And you'll see rape is then a more common charge than murder. So you have to control for the differences in frequency, in this case, for these three metrics. The other thing you'll know is that and the reason why you have to do that is, or the reason why they go out so far is that if you look at the axes labels, they're significantly different now. And so by normalizing them and standardizing them, we can not only compare percentages to larger numeric values, but we're also controlling for the fact that assault is a more frequent arrest than rape or murder. Another consideration is when we're compressing our variables into a lower dimensional space, there's going to be some variance that remains unexplained. So in this example, we had 4 variables, and you can see that they're represented in the x-axis, 1, 2, 3, 4, and each of them explains some percentage of variance within the data. But you can see that there's a law of diminishing returns. So as you go further down, you get less of the variance explained. But you can get most of it explained in the initial variables and initial principal components. And so some of that is kind of figuring out how much should you, how many principal components to use. And so the next slide talks a little about that. Yes, every time we add a principal component, we will get a little more variance explained. But at what is the cost of that? At some point, if we had 4 variables and we used 3 principal components, we didn't really simplify our model that much. And in fact, we might have made it a little more confusing. In the example I used with education, we started with 75 and we brought it down to 4. So we were able to capture most of the variance, but we did lose some. And so this is a bit subjective. It kind of depends on how much you're trying to capture. But a useful tool is the elbow plot, and it'll help you understand like where is the point of diminishing returns. Like when do you want to start thinking about dropping the remaining component. So you look for the crick, that sharp bend in the curve, and that's when you should cut the line off. So the next technique we'll talk about with unsupervised learning is clustering. So clustering is used to create segments or groups within a data by defining which observations may go together or which ones may look different. Some of these applications include targeting users or thinking about what products to offer. So again, you can't create an individual phone plan for everybody, but perhaps you can come up with enough, a few options that satisfy most people. So you think about the family plan or maybe international plan and so on and so forth. Another example is lookalike analysis. So again, the recommendations engines, people who look at the same items will probably purchase the same items. People who like a certain type of TV show will probably like another type of TV show. Another example is experimentation design. So often you don't have the opportunity to set up a perfect test and control. And so by doing clustering, you can start seeing, okay, what observations look similar enough so that you can then do some sort of comparison across those metrics. And of course, it's also useful for data exploration, just by helping us identify and visualize patterns. So two of the common techniques we'll go over are k-means and hierarchical clustering. So the main distinction is that k-means, as the modeler or the machine learning engineer, you have to decide how many clusters you want. And that can be a bit of an art. Sometimes there's external factors like how many sales reps do you actually have to go deal with customers or some other external constraint. But from a modeling perspective, how many clusters is determined by you. Hierarchical clustering does not preset the model cluster number. Rather, it will go forth and do the clustering, and then it'll kind of lay out this menu or a visualization for you to see, okay, how does it look when we use 1 cluster, 2 cluster, 3 cluster, so forth, so on and so forth, all the way up to n. So it does it more on the back end, whereas k-means you do that on the front end. So at the moment, it might sound very similar, right? Like PCA, we're also trying to simplify and reduce. Clustering sounds like we're also trying to look for similarities and reduce. The key distinction is that PCA is trying to reduce highly dimensional data to make it easier to summarize, whereas clustering is partitioning your data by looking at observations and comparing them to each other and saying which ones look similar to each other. So if you look at this table structure that we use to identify data, if you think about columns as being the features and then the rows being observations, individual data points, which side do you think represents PCA and which side do you think represents clustering? And you can take a moment to think about that. And this is assuming the blues are very similar to each other, whereas the kind of beige tan color is very similar to each other. So hopefully you decided that PCA was the one on the left, and that's again because columns are features. So the 3 blue columns would go together, whereas the 3 tan columns would perhaps go together and create 2 principal components. On the right, you have clustering. So again, the rows are individual observations, and so you would take maybe the first 2 tan rows and the bottom tan row and put them together and say this is one group. Maybe it's by ethnicity or by gender or by Northern California, Southern California, and the blue points, those 3 continuous rows are another group. So it's quite similar in the sense that we're trying, PCA and clustering, it's quite similar in the sense that we're trying to simplify and reduce, but the distinction is the orientation of feature versus observations. And so keep that in mind as you get familiar with both techniques. So k-means clustering, the goal is to partition our data into k distinct clusters. That's where the k comes from. And so again, it requires the modeler to set that k. Something you might have heard before is the idea of something that is mutually exclusive, collectively exhaustive, and that's represented in the text below in a more mathematical, logical way. But effectively, what we want to do is have every single data point fall into one cluster, which applies to the collectively exhaustive rule. And then we also want them to be mutually exclusive, meaning that no data point falls in two clusters. So only one cluster. Each data point must fall only to one cluster. And so as a result, you'll end up with something like on the right, where we've separated all our data points into 5 distinct clusters. You'll see that no data point is sitting in 2 clusters, and then also no data point is unclustered. And so that is mutually exclusive as well as collectively exhaustive. And as a result, if we do this, we can then say which data point looks like which group, and that's ultimately the goal in clustering. So if each group should look alike, how do we know how alike are they? So the goal is to minimize the variance within a cluster, right? So if we have 5 clusters, we want all the members within each of those 5 clusters to be quite similar. We want them to be quite homogeneous. And so we can measure this by, say, tracking the within the cluster variance. And how do you define W? So the most common metric we use is Euclidean distance, which is basically just like the straight line between 2 objects as the crow flies. And so when we're able to plot something out like we did above earlier on a scatter plot, we can literally go and measure that distance using geometry. And so the formulas below then help you figure out how to optimize the Euclidean distance between data points and something called the center of the cluster, which is known as the centroid. But let's go into the algorithm. So mathematically, there's a lot of ways you could group your data, right? So an example here is if you have 100 observations and you want to break them into 5 clusters, if you were to just do this exhaustively, there would be 10 billion variations. So 100 to the power of 5. Luckily, we have an algorithm that will allow us to do this partitioning and grouping without going through all variations. And so we'll talk through this really briefly, but and it'll be easier to understand later as we go through some examples. But you start by randomly assigning a number, so 1 to k. So let's use the example above with 5 clusters. We will want to assign our 100 observations into all of them would be randomly assigned into a cluster, one of the 5. And then we would start a iterative loop where we first look for the center of each cluster. So again, we have 20 random data points, and we find what's the middle point of all those 20 data points. And that will become that cluster's centroid. And then you do this for all 5 clusters. So you find 5 centroids. And then what you do is then step back from the centroids, go back to the observations and say, okay, this cluster, this observation, which centroid is it closest to of the 5? And if it's already closest to the centroid that it's a member of, then nothing changes. But if there's another centroid that's closer to it that's in a different cluster, we update that observation to be in that cluster. And you update those observations, again, using Euclidean distance to determine what's closest, and then you repeat again. So that's a lot of words, but here's a visual way of seeing this. So you'll see that this only iterates 10 times, and there's 3 clusters, and the stars represent the centroid. And so what happens is initially the red is kind of on the left, but it very quickly moves north and upwards. And as a result, the boundary line starts moving. And the reason it moves up is because there's a few data points way up there, right, in the 20s and the 15s. And so that pulls that red centroid up. And as it moves up, some of the observations that are more in the middle, maybe at the 5 along the y-axis, they start getting eaten up rather quickly by the green initially, and then by the blue. And you see as the blue observations start creeping towards the middle and slightly upwards towards 5, the blue centroid also moves in and to the left. And so that's just done on an iterative basis, and it goes back and forth. So let's break it down a little bit more. So you see initially you have this data, this visualization that we saw earlier. The first thing you do is randomly assign. So you end up with this potpourri kind of salad of colors. And then you create 3 centroids because we want 3 clusters, right? And we predefine the number of clusters we want. And so those centroids are put in the middle of all their members. And because we randomly assign the members, all the centroids kind of start in a very similar location in the middle of our plot. However, they are a little different, and you can see that then all the members in iteration 1 step 2b get updated to align to the closest centroid. And that's where the gold tan goes up, the green to the bottom right, the pink to the bottom left. The next step is the centroids start moving. So the gold sees that all the gold observations are up there, so it moves up. All the pink and green start moving down because their observations out there. They also start pulling apart left and right. And so you end up with 3 kind of more unique clusters. And then it continues to do that. And you'll see there's a few observations in the middle. In particular, hopefully you can see my mouse, but there's 3 gold data points that finally get sorted, 2 that go green and 1 go pink. And it repeats until basically the assignments stop changing. And at this point, now you have kind of a clear boundary line. Anything that is north of a certain point becomes kind of tan and gold. And then below you have green and pink. And then there's kind of a north-south boundary line where everything on the left becomes purple, and then everything on the right becomes green. So some of the things you have to be aware of is because you are randomly selecting how you initialize your algorithm, you might end up with different final cluster assignments. So you'll see on the right, you have 6 clustering results, and you'll see 4 of them look quite similar, right? And they all have 235.8 at the top, but the colors are different, right? So it kind of depends on what they initially started as, but what happens to the chart at the top left and then at the bottom right, the 320 and the 310, is that they got stuck in a local minima. And that's partly because things started out randomly and they optimized themselves, but it looks like what mostly happened is that the bottom 2 clusters that typically we had 2 cluster for became one giant cluster in both cases, and then the 2 clusters at the top started fighting for the remaining observations at the top of the chart. And so what you might want to do is just run this many times, and there's a parameter within the R code that lets you do this, but this will make sure that you don't get stuck in a local minima. The other thing that we've mentioned is that you have to set K in the beginning, and this can be fairly subjective. So having an elbow chart to measure the variance, which is what those numbers at the top represent, will help you do that. And so you would basically run, say K equals 3, measure the variance, K equals 4, measure the variance, K equals 5, measure the variance, K equals 6, measure the variance, and then look for that variance. And what you want to see is a big fall each time you increase K, but when the curve starts bending, when the variance is not falling too much, that means that you probably are not you probably don't need to increase the number of clusters, but what's happening is that adding additional clusters is not bringing the homogeneity of the cluster group higher, right? So that you may have a group of people and you break them up twice, or you break them up once and you have 2 separate groups of people. But then if you take one of those subgroups and you break them up again, they might actually still be the same, very similar types of people. It doesn't actually pay off to do that again. So using that elbow chart will help you do that. The next technique is called hierarchical clustering. So this is very different as opposed to k-means where you had to set that number. Hierarchical clustering will kind of lay it out all for you like in a menu, and then you can kind of start looking at the patterns and then decide what number of clusters to use. So it's displayed in this funny word called dendrograms, and it's basically this upside down tree format. And again, like the tree-based models, the leaves are the individual observations, and as they start looking for similar observations, they become branches, and then it keeps going upwards. So the lower that join occurs towards the bottom of the chart, the more similar observations are. And depending on where you cut the branches, that's how many clusters you have. So on the left, you don't cut it at all, so everything is green. In the middle, you cut across horizontally, there's 2 cuts, so you end up with 2 clusters. You have the pink and the green. And then on the right, you cut it further down, and there's 3 cuts across the tree, so then you end up with 3 clusters. And you can see that yellow and green are a little more similar than pink. Continuing on that, the key variable here is to pay attention is the height. So if you look at, for example, on the dendrogram, 9 looks like it's part of one school of branches. But then when you look at the scatter plot on the right, note that 9 is actually pretty far away from 2 and 8 and 5 and 7. And that's how you should look at it. So really look at the height. The further higher up that join is, the less similar it is. So let's actually walk through the algorithm itself. So you're going to have to define a dissimilarity or similarity score. And this again uses Euclidean distance because we are measuring geometric distances. And we'll look at all the observations. And you start by treating each observation as its own cluster. And then you start out with it. You start by then joining similar clusters together, and each time you join a cluster, you obviously reduce your number of clusters by 1. And you keep doing this until you end up with 1 cluster. So you started out with 100 observations, you would have 100 clusters. You want to end up in a place where you have 1 cluster on 100 observations. So here's a visual example of doing this. So you start with the data set at the top left, and then you start comparing each observation to each other. You see that there's a couple that are pretty close to each other, 6 and 1 and 5 and 7, and it looks like 5 and 7 are a little closer, so they become a cluster, and you draw a red box around that. Then you go back to 6 and 1, and you draw a blue box around that. And then you start saying, okay, now that these leaves are now a branch, which leaves are close to each other, or which leaves are close to a branch. And so it looks like it could be 4 is close to the 6-1 branch, or 2 could be close to the 6-1 branch, but it looks like 8 is the closest. So the 8 leaf joins with the 5-7 branch and forms a brand new branch, this green box, and they become a branch. And you repeat this so on and so forth, and it looks like perhaps 4 or 2 are the next closest. And yeah, so we saw that 6 and 1 joins with 4, and so they formed a branch here, and then looks like 3 was closer to that, and then 2 falls closer to the other branch. So that's how the hierarchical clustering algorithm works. Again, the key parameter you'll have to set is the dissimilarity metric. And there's a few options, but basically you're going to be at a leaf point, you're just comparing leaf to leaf. But at some point you have a bunch of observations that form a branch, and you need to compare that branch to another branch which is made up of its own set of observations. And so here are some ways of measuring that. So you're going to measure all the pairwise observations, and if you use the max, that's complete. If you look for the smallest one, that's single. If you do an average, that's just average. And then you can also look at centroid, which would be kind of finding that center point of that group as opposed to the average. And depending on which technique you use, you can end up with vary-looking dendrograms. So if you look at this example here, we have average linkage, complete linkage, and single linkage, right? So the single linkage on the right, you'll see that it's just single linkage is looking at the closest observation. So it's going to be a little greedy, and you'll see there's a lot of one leaf type joining branches, because each time there's a single leaf that's close to anything, a branch, it'll just pick it up and form a new branch. And you can visualize a tree with a lot of one leaf branches. By comparison, average link, you can see it starts out, it goes much more broad, and it will link up much later on, right? And then finally, complete linkage looks like it does a lot of, first, it identifies a bunch of individual two-leaf branches, and then it merges them together. So to summarize, there's a lot of things you need to think about when you're doing clustering. One of the most important steps is to do standardization of features. This will help you with performance. You just need to be careful that it may also be muting some of your key clusters. Some key questions to ask, again, are how many clusters should I use for the k-means? You should also be thinking about the variance within the clusters, which will help you decide how many clusters to use. For hierarchical, you're thinking about what dissimilarity or linkage measure to use. And then once you do that, you are thinking about when do you want to cut your dendrogram, right? So depending on how high up you go on the tree, you'll have less clusters. If you go lower on the tree, you'll have more clusters. One thing you note is that forcing everything into a cluster may result in some clunky clusters if outliers exist. So if you go back to the idea of the income versus education. If you have one person who's a billionaire, that one data point will throw off all your other data points, because whether you use k-means or you use hierarchical clustering, it's going to create some very stretchy clusters. So it might make sense to remove that, because yeah, maybe that one billionaire is not representative of a cohort of students or a city. So it may make sense to remove. You may also explore using something that kind of goes beyond the scope of this lecture, but mixed models. So before we were saying every member must belong to a single cluster. There are mixed models that look at this more probabilistically. So it says, instead of saying you have to belong to cluster A or cluster B, it might say that this data point is, maybe 70% likely in cluster A and then 30% in cluster B. So it tackles it with using softer margins as opposed to a hard margin. So let's talk about coding. So you can use PR-comp to do principal components analysis. You'll see there's no longer that y tilde x syntax because we don't have a y variable. So you just need to feed your data in. You need to set your scale to true, again, to normalize and standardize your data. And then what will come back, you can use biplot to visualize the PCA, which is what we saw with the US arrest data. There's also some parameters that might be useful for you to make sure that your data is scaled and centered. So by looking at center and scale, and then you also might want to be looking at rotation to see what are some of the loadings, what are the weights for your principal components. For k-means clustering, it's very important to set your seed. So remember, the first thing that k-means does is randomly assign variables to clusters. So in order to make sure your work is reproducible, make sure you set your seed so that when you randomize something and someone else randomizes something, it's the same. Otherwise, you're going to end up with very different clusters. So the key function, again, no y tilde x, you just feed in your data. K is the very important variable where you need to decide how many clusters you want. And again, there may be external things. But that's on the modeler to decide which K to optimize for. And again, often you'll use the elbow chart. So you'll do this for any number of Ks, and then you'll see which one works better later on. One thing to keep in mind is also the end start parameter. So again, because things are randomly assigned and you might get stuck in a local minima, the k-means function will actually do this multiple times to make sure that it does not get stuck in a local minimum. So you can use a higher number to make sure that that does not happen. And there's some methods that are useful, including cluster, which will show you, how were your individual data points clustered and grouped together. Hierarchical clustering uses hclust, and here you have data where you feed your data in, and then you have method, which will determine your linkage measure. You can use plot to see the plots, and then use cut tree to see the final clustering assignments. Let's talk about weekly assignments. So you do not have any labs, you do not have any quizzes. There is something in the book if you'd like to go do some self work, but there's no graded component. You do have a discussion board, and you can earn some extra points if you participate a lot. But this time is freed up so that you can be working on your final project. So please make sure you find the time and space to do that. But otherwise, you have reached the end of the course. So congratulations. Just give yourself a pat on the back for all that you've covered, learning to code and do machine learning, and from regression all the way now to unsupervised machine learning algorithms. Hopefully this has given you some intuition and some applicable use cases for using machine learning. And I wish you all the best on your final project and in your further pursuit of machine learning.